Jai Hind, welcome to class of Satellite and Radar Systems. This is Unit 2, Part 3, and we'll be talking about satellite link design today. First of all, we need to understand what do we mean by a link and how to design it in respect of satellite communication. We know that link is the transmission path between 2 points, right? It is a connecting point between a point A and point B. Those can be involved in communication, right? So whenever we design a path for a satellite communication, that is from transmitter to receiver, here in this case that would be from transmitting earth station to satellite, and then from satellite to receiving earth station, then that link has to be designed considering so many parameters, and those needs to be calculated mathematically, right? So designing of that link involves so much of calculation, planning, and it involves so much of expenses within it. So satellite link design is not an easy process. It's a lengthy task where your government is involved, so much of calculation, assumptions, predictions are involved, and we do design a path, right? The question is, what are the parameters that needs to be included when we design a link? So when a satellite is built, the cost of launching or designing a satellite includes so many things, like that involves how much the weight of the satellite would be, how much DC power is generated, right? At what frequency the satellite is working, and finally the multiple access techniques that we are using. So these are the 4 basic parameters that needs to be observed mathematically whenever we talk of designing a satellite or designing a satellite link. Now many of the times we'll encounter with the term link budget or link margin. So link budget will also involve the expenses used in this, right? And link margin will give us the tolerance, how much, what parameter can be tolerated. So in totality, the main thing here is in what respect we do calculation. That sole parameter here considered is the power. So in link design we'll be talking about power calculations, right? How much power is transmitted from a transmitting antenna, that could be the earth station here, and how much it is received at satellite, or if we are considering the transmitting power at the satellite, then how much power is received at the receiving earth station. So all those calculations need to be done in terms of power. So this was the overview how we are going to start with our studies in link design, right? Let's move forward. So we'll be talking about introduction to satellite link design, the basic transmission theory. By transmission theory, we'll be talking about power transmitted and received, and system noise temperature. Whenever we are talking about power, then power of the actual message, that is useful information, has to be considered, and power of the noise also has to be considered. The reason being, in any communication system, whenever we talk about actual signal power, the sole signal power cannot be considered alone. We have to consider the effects of noise as well, right? Satellite communication is for long distance communication. Here the wireless channel is huge. The length of the wireless channel is huge. We are getting transcontinental, transoceanic, intercontinental communication. So there are the path here is so large that incorporation of noise is something we cannot avoid. Although the thing is, in any kind of communication system we cannot avoid noise, so noise has to be studied. And whenever we calculate signal power, the sole signal power cannot be calculated alone. We have to calculate it in respect of noise power as well. So what we usually do is we calculate signal power, we calculate noise power, and usually its ratio is calculated, which is in analog signals we call it like we calculate it in terms of SNR, that is average power of signal by average power of noise. So noise is something which is unavoidable. We cannot just avoid noise anytime. So noise temperature is something which we'll be studying here. So that is what I wanted to talk about, right? Let's move further. The design of a satellite communication system is a complex process, true. It requires compromises between various factors to achieve, best performance at an acceptable cost. So we know whatever we talk with in respect to some reference we need to talk. So let's talk about a communication satellite launched in geo orbit. For that communication satellite, the cost to build and launch is approximately $25,000 per kg, right? So we can imagine how much of amount we are spending in launching and making a satellite, right? Now the weight of a satellite is driven by two factors, that is, these are the two most important factors: the number and output power of the transponders on the satellite and the weight of station keeping fuel, right? As much as half the total weight of satellites intended to remain in service for 15 years may be the fuel, right? That is, any communication satellite launched in geo orbit, it provides its services for approximately 15 years. So the cost that we use as an input, like to make the satellite and to launch the satellite, the revenues has to be generated in the rest of the 15 years so that we can compensate the money which we have involved in making the satellite and launching the satellite. So budget is an important factor here, right? Three other factors that influence system design include the choice of frequency band, atmospheric propagation effect, and multiple access technique. Main things: number of output power of the transponders. Number and output power. How many transponders? What will be the power of transponder? Number two, weight of the station keeping fuel. This factor is simply the weight and power, right? Apart from these two, we have what frequency band, what are the atmospheric propagation effects, that means we are talking about noise, and multiple access techniques, FDMA, CDMA, TDMA, which technique is used. So these are the factors, right? So the information carrying capacity of any radio communication link is determined by RF power at the receiver input, true? So RF power is an important factor. Now we need large antennas to receive weak signals, and the signals from satellite in geostationary orbit are invariably weak, true? Geostationary is at a height of approximately 35,786 kilometer, which is a huge distance, a large distance, right? Early satellites were small and light, carrying small antennas and transponders with low output powers. If we talk about early satellite, nowadays they were not capable of carrying weak signals, right? So that time the earth station antennas had to be large enough to catch those weak signals, that is approximately 25 meter diameter, and high power transmitters were needed. But these days we have even reduced the antenna size, this diameter, to very small. We have the application of VSATs, very small aperture terminals. We use direct to home parabolic dishes. Those are like approximately 0.5 meter diameter, right? So to understand the link design, we need to understand the basic transmission theory. All those calculations we'll be doing in terms of power, so we need to understand the basic transmission theory here, right? The calculation of power received by an earth station from a satellite transmitter is fundamental to understanding of satellites. So power received is the factor, right? So we'll be in this section, we'll be discussing about two approaches, that is use of flux density and the link equation. What is this link equation? Let me give you a brief overview. Here in this link equation, all those calculation will be done in terms of power. What will be the relation of my received power with my transmitter power? What will be the factors involved that will be causing attenuation in the received power? So that calculation, the final equation that will be receiving, equating our transmitted power and received power, that has to be considered in link equation. That will be my link equation. So for this, let us consider an isotropic radiator. Consider there is a spherical radiator which is radiating energy. This is a sphere which radiates isotropic, like this is radiating uniformly in all direction. This is a uniform isotropic radiator, let's suppose, right? So it's EIRP. Here EIRP is effective or equivalent isotropic radiated power. So the power radiated by the transmitter, it is given in terms of P subscript T, that is transmitted power. Now let's suppose it falls on a receiver of area A meter square, right? So what will be the flux density? We know that flux density is power per unit area, right? When flux density is power per unit area, so we can calculate it in terms of watt. That is power, unit of power is watt, and per unit area, that is meter square, right? And let's suppose the distance between the transmitter and the receiver is r meter. So these are some assumptions that we are taking, and using these we'll proceed in further calculation. So here in satellite communication system, there are two types of power calculation. Those are transmitting power and received power. True, we just discussed, and we have to relate these two power. In general, these calculations are called as link budget calculation, right? And whenever we calculate power or noise, this calculation will be carried out in decibel. Whatever, if you get it in watt, we will be converting it like 10 log to the base 10, 10 log to the base 10, and we will be converting it into decibel. Usually it is expressed in decibel, right? An isotropic radiator antenna radiates equally in all directions, but it doesn't exist practically, which is true. This is some idle antenna that we consider. It is just a theoretical antenna, true. We can compare the performance of all real antennas with respect to this antenna, true. Now let's talk about the basic terminologies that we'll be using here. Power flux density. What is power flux density? Assume an isotropic radiator is situated at center of a sphere of radius r, right? We know that the power flux density is the ratio of power flow per unit area, ratio of power flow with unit area. So for sphere, it will area is 4 pi r square. So power flow, it's defined in terms of PS, where PS is the power flow, true, and power flux density in that particular direction, but its maximum value will be in one particular direction only, true. That holds true for every practical antenna, because practically there is no isotropic antenna. So next term is gain. What do we mean by gain? Gain of a practical antenna is defined as the ratio of maximum power flux density of practical antenna and power flux density of isotropic antenna. Like if we consider that a practical antenna is radiating in a particular direction, and let's consider the flux density in the direction of its maximum radiation. That will be represented by this term which I put in numerator, and replace that with an isotropic antenna and what it will be radiating in all direction. That flux density I use in denominator. So ratio of these two entities will give me the gain of the antenna, right? Where this is the maximum power flux density of the practical antenna. True, practical antenna will be radiating in one particular direction, maximum radiation will be in one particular direction. We know that like these are the antenna lobes. We know this is the direction of maximum radiation intensity. We have the major lobe in one direction. So in that respect it is explained, right? And is the power flux density of the isotropic antenna, and sorry, this is the power flux density of the isotropic antenna, right? Now what is equivalent isotropic radiated power? Equivalent isotropic radiated power, EIRP, is the main parameter that is used in measurement of link budget. What is EIRP? EIRP is basically P into G, because only we cannot just simply go with the power transmitted, we have to consider the gain of the antenna as well, right? Considering my antenna to be a practical antenna, I cannot simply go with just PT or PS, that is transmitted power or flux density. I have to consider gain of the antenna as well, where G is the gain of the transmitting antenna and PS is the power of the transmitter. So this is G into P, and when I calculate in decibel, this is in what? When I calculate in decibel, that is 10 log to the base 10, this multiplication gets converted into plus, right? EIRP equals to G plus P decibel watt, right? So the difference between power sent and at one end and received at receiving station is known as transmission loss. True? I am transmitting at this end 100 watt. What I receive is 60 watt. If my PT was 100 watt and my PR is 60 watt, what will be the relation between my, so what is the loss here? Loss here is of 40 watt, right? Simple. So this is my transmission loss, this 40 watt is transmission loss, right? So basically in link design calculation, I am calculating this thing, PR equals to, here in this particular case with what factor my PR and PT are related. Here they are related with 0.6, a factor which is 0.6, right? So these could be constant losses or variable losses. The losses which are constant, such as feeder losses, these are unavoidable, we cannot avoid these. Are constant losses, no matter what precautions we might have taken, these losses are bound to occur. True? Another type of losses are variable losses. Now these variable losses depends on atmospheric effect, because these are not stable all the time, these keeps changing, right? Variable losses, the sky and the weather condition. We face so much of rain attenuation in case of satellite communication, which we'll be discussing in further study, right? So let's see it with the help of a picture. This is my transmitting antenna, which is spherical isotropic antenna, isotropic source. EIRP is PT watt. It is radiating P subscript T. With P subscript T I am showing the transmitted power, right? Now how much amount of power falls on it, that is calculated in terms of flux density, that is power per unit area. So this is watt per meter square, and the receiver is receiving, that is denoted by PR, because PR and PT are two different terms, because there are losses and attenuation involved. So receiving antenna has area, suppose A meter square, and receiving antenna has a gain of GR, that is G subscript R, right? So the power received by an idle antenna with an area A meter square, incident flux density F is PT by 4 pi R square. True? This is 4 pi R square, watt per meter square. True? received power is PR, and flux into area here. Flux into area will give you total power, because flux is power per unit area, and when power per unit area is multiplied with total power, I get the total power value. This is PTA by 4, sorry, pi is missing here, I must put 4 pi r square watt, right? So power received is, total power received is flux into area. Flux is because power per unit area multiplied by total area, that will give you the total power received, right? If we have an ideal receiving antenna with aperture area of A, area of meter square, this is square, we would collect power PR watts given by this. Now reduction in efficiency. Now there is a thing that we have to always consider. Suppose this is my receiving antenna, right? All the incident waves falling on this will not be contributing to the received power. There must be certain amount of power that will be falling on edges, which get scattered, which get reflected, which get absorbed. So I cannot just consider the complete aperture of my receiving antenna at the time of considering power, right? I have to consider the effective aperture, that is the actual area which is contributing in power received. So that is called as like effective aperture, right? Where AE is the aperture efficiency. AE equals to eta A AR. What does it mean? This is the actual area and this is the efficiency. Like suppose the area was 100 meter square, right? And but how much we receive? This total area is not contributing. Only 30% of the area is contributing. So efficiency here needs to be multiplied with the total area so that we get the effective area, right? Where A is the aperture efficiency of the antenna, and the aperture efficiency accounts for all the losses between the incident wavefront and the antenna output port, right? That is PR equals to PT GT AE by 4 pi r square. So see what we are proceeding towards. We are proceeding towards more precise calculation. Initially power could be considered only P, but no, then we have used a factor that is G. Power will be equals to power transmitted will be power, then we have to consider gain, and now apart from power and gain we have to consider another factor which will be the effective aperture. So PT into GT into AE, and this is the area of the sphere, right? So this is power received. So we are moving towards more precise calculation, right? So a fundamental relationship between antenna theory is that gain and area of an antenna are related by, this is a fundamental equation for any antenna engineering, that is gain equals to 4 pi AE by lambda square, where this is the wavelength in meters at the frequency of operation, right? So I can rewrite my equation as PT GT GR by 4 pi by lambda whole square, right? I can rewrite my equation like this, right? This expression is known as the link equation. So this comes out to be my final expression for the link equation. So this is something important. We were calculating this actually since the beginning, right? We wanted an equation that would be relating my transmitted power and received power, right? This expression is known as the link equation, and it is essential in calculation of power received in any radial link, right? Collecting the various factors, we can rewrite the expression as power received is equals to PT GT can be written as EIRP, and GR is the receiving antenna gain, and 4 pi R by lambda square is my path loss. So power received is EIRP multiplied by receiving antenna gain divided by path loss. So in communication systems, decibel quantities are commonly used to simplify equation, that is if I rewrite this expression in terms of decibel, then these multiplication I will write in terms of plus and this division I will write in terms of minus. So I can rewrite my link budget equation or link equation as PR equals to EIRP plus GR minus LP in decibel watt. Now let's expand these terms. EIRP can individually be written as 10 log to the base 10 PTGT in decibel watt. True. GR receiving antenna gain can be written as 10 log to the base 10 4 pi AE. AE is the effective aperture by lambda square. True. And path loss can also be rewritten as this. Right here I can, this will come in front and I'll get 20 log. So I can rewrite my equation where now like along with the path loss there are other losses also which I'll be considering in my final expression, as this is the final expression for my link budget equation, that is more precise form of the equation. See, this is my link equation, true. When I write in like decibel, this is my link equation, and more precisely including all other parameters or more of the losses that we actually face in atmosphere. So EIRP plus GR LP. So losses has to be considered as subtraction. So LP is my path loss. I will be considering one more loss which will be the attenuation loss in atmosphere. Attenuation is an important factor that we cannot just avoid in any kind of communication. Then LTA. Here LTA is the losses associated with transmitting antenna. There are certain losses which are inbuilt in the transmitting antenna as well, which we cannot avoid. So those are my LTA. And what is LRA? LRA is the losses associated with the receiving antenna. What are losses associated with the receiving antenna? Those are some inbuilt losses that cannot be avoided. So those also has to be considered. So this is the more precise form of my link budget equation, right? Or link equation, right? Link budget calculation. So this is explained with the help of a picture. If I summarize my complete lecture today, now suppose this is the satellite, the power radiated by the satellite will be PT and EIRP will be PT into GT, and if I consider losses associated with transmitting antenna, then the losses are LTA associated with transmitting antenna. This is the path through which it is traveling. So in the path it will be facing some path loss expressed by LP. Because of rain and atmospheric condition, there will be atmospheric losses indicated by LA. This is my receiving antenna. So I have to consider the gain of the antenna, which is GR. The losses associated with my receiving antenna, LRA. Then how much power it is received, PR. The first block of any receiver is my low noise amplifier, LNA, which will chop off the noise and will amplify the low power signals. So this is my low noise amplifier, right? So this shows my complete satellite link, summarizing all the things that we have calculated here, that is showing relation between the transmitted power and received power. This picture summarizes all the calculation that we have used in my link budget equation, right? So this is the final picture that helped me calculate my PR. Let's see it again. PR equals to EIRP, which is GT to PT into GT, right, into GR and all the losses. So this was in watt, and when I calculate in decibel, plus 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 minus minus, path loss, attenuation losses, losses associated with transmitting antenna and receiving antenna, which is expressed with the help of this picture here, right? So that's it for today. These are the references which I have used. Thank you.